minimum starting speed. Now, as a pump is started, it does not deliver water until enough head is developed to raise the water to the desired height. So, according to the Euler's equation, so energy transfer per unit mass that we can write as Euler's head, that is the energy transfer per unit weight. So we can write it as VO square minus VI square divided by 2G plus UO square minus UI square divided by 2G plus VRI square minus VRO square divided by 2G. Now, till the pump starts delivering water, so there is no flow from the eye towards the periphery. So at that time, when we start the pump, the velocities of flow, the fluid velocities are zero. Okay. So at that time, only the centrifugal pump is applied on the liquid. So the flow will start as soon as that centrifugal head developed become equal to the total head. So now when we start the pump, there are no velocities. That means this head is not there, this head is not there. Only the centrifugal head is available. So when we start the pump, the head developed, the Euler head is only UO square minus UI square divided by 2G. Okay. So the minimum head required if is H. Okay. So then I can write this UO square minus UI square divided by 2G equal to H upon hydraulic efficiency. Okay. Or this I can write as, now UO I can write as pi DON divided by 60 square minus pi DIN divided by 60 whole square is equal to 2GH divided by hydraulic efficiency. Now further from here I can write pi n upon 60 square into dO square minus DI square equal to 2GH divided by hydraulic efficiency. Now further from this formula I can write N minimum, that is the minimum speed of the pump to develop a head H, that is equal to 60 divided by pi 2GH divided by hydraulic efficiency into dO square minus DI square. Okay. Now this term is in under root. So this is the my formula to develop a minimum head of H with a minimum speed Nmin. Okay. So this is the formula for minimum starting speed to develop a head H. Then next is the limitation on suction lift. Limitation on suction lift. Okay. Now the suction or negative pressure is developed at the inlet of the centrifugal pump, that is at the eye of the impeller. So this suction pressure or this negative pressure depends upon the height of the pump above the sump level. So that is as similar as to the draft tube of a reaction turbine. Okay. So when this absolute pressure is reduced to a value equal to the vapor pressure of the liquid, that is water, at room temperature, the water starts evaporating. The bubble starts forming. So when these bubble reaches the region of high pressure, then they collapse over there and vacuum is created. When they collapse at certain location, a high pressure wave is created, so that strikes on the surface of the veins or the casing. So that produces the pits or cavities on the veins. So this whole process is called cavitation. This is called cavitation. Okay. Now we have to avoid this cavitation in the centrifugal pump. So therefore, it is necessary that the pump is to be fitted at such a height that absolute pressure or negative pressure at the eye of the impeller does not fall below the vapor pressure of the liquid. Okay. So at the eye, the pressure should be more than the vapor pressure of the liquid. Okay, at the eye of the impeller, the pressure should be more than the vapor pressure of the liquid. At the least, it should be equal to the vapor pressure of the liquid. Okay, so that is the maximum value of suction lift we can find out. Okay, that is the maximum value of suction lift we can find out. Now, if we try to apply the Bernoulli's theorem at, see this diagram, uh, over here, at section B and section A. Section B and section A. B is on the I side of the impeller and A is at the sump level. So now if I try to apply the Bernoulli's theorem at these two sections, so at section B, I can write now the pressure head, that is HMS plus HS plus Vs square divided by 2G plus the frictional loss in suction pipe. This is equal to PA divided by W or rho G plus the elevation head, that is the datum, plus the velocity head, that is 0. Okay. Now this HMS now I can write as pressure on suction side divided by W. Okay. Now this value of PS should not fall below the vapor pressure of water, that is PV. Okay, so at the least this value should be equal to PV. Okay, so now I put this value of PS over here, so I can write PV divided by W plus HS plus Vs square divided by 2G plus HFS equal to PA divided by rho G. So from here I can find out now HS, that is equal to PA divided by rho G or W minus PV divided by rho G plus Vs square divided by 2G and minus, sorry, these two signs are minus. This is minus and minus HFS. Okay, so the suction height should not be more than this value of HS. So I repeat it again. The suction height should not be more than this value of HS to avoid cavitation. ठीक है? At this value of HS or below this or more than this value of HS, there is a problem of cavitation in the centrifugal pump. Okay, so this is the maximum value of HS to avoid cavitation. So that puts the limitation on suction lift, that is the suction head. Okay, so this is how we can decide the suction lift. Okay, or the suction head, you can say. Net positive suction head, that is NPSH. So the net positive suction head is defined as the value of velocity head, okay, plus the pressure head at the center line of the pump inlet above the vapor pressure head of the liquid. Okay, so NPSH is the value of velocity head plus pressure head above the vapor pressure head of the liquid. Okay, so now I can write this as NPSH, that is equal to Vs square divided by 2G plus Ps divided by rho G minus PV divided by rho G. Okay, so this difference is NPSH. Now you can also see from one above equation, uh, that is this one. Okay, so from this equation I can write PS by W, that is rho G, okay, equal to PA by W minus HS minus Vs square divided by 2G minus HFS. So I can write from this equation as PS divided by rho G is equal to PA divided by rho G minus HS minus Vs square divided by 2G minus HFS. Okay, so now from here you can find out PS divided by rho G plus Vs square divided by 2G equal to PA by rho G minus HS minus HFS. Now you subtract PV by rho G from both sides. Okay, so I can write PS divided by rho G plus Vs square divided by 2G minus PV by rho G equal to PA by rho G minus HS minus HFS minus PV by rho G. Okay, so this term is my NPSH. So this should be equal to NPSH. This is another formula for net positive suction head. Okay, so this is term G, rho G. Proportions for centrifugal pump. So first is the speed ratio. Okay, so it is the ratio of tangential velocity of impeller at outlet. Tangential velocity of impeller at outlet to the quantity under root of 2gh. So I can write this speed ratio is equal to UO divided by under root of 2gh. So this is the speed ratio for centrifugal pump, and its value lies between 0.95 to 1.30. Okay. Then the next term is flow ratio. Okay. So it is the ratio of flow velocity outlet, that is VFO, to the quantity under root of 2gh. So I can write Kf, that is equal to VFO divided by 2gh under root. This is flow ratio. Its value lies between 0.1 to 0.25 for centrifugal pump. Another is the pressure coefficient, that is Cp, that is 2gh divided by UO square. Okay, this is also equal to 1 divided by Ku square. That is another coefficient. Okay, there is one ratio that is called diameter ratio. That is dO divided by di. So the ratio of outer diameter of the impeller to the inner diameter. So that is diameter ratio. Okay. Then vane angle at outlet. Okay. So the best for best efficiency, the value of outlet vane angle, that is beta O. So it is from 20° to 30°. And on our average, you can say this value is 25 degrees. Okay. And then the number of vanes. Normally in a centrifugal pump, the number of vanes should lies between 6 to 8. The numbers are 6 to 8. So these are some important proportions for centrifugal pump. Okay. Now to develop the high head, you have to increase the value of UO. Okay. So, however, when we increase this value, the stresses, the centrifugal stresses are also increased in the impeller. Okay. So, that limits on the value of increase in UO. Ultimately, that limits on the value of the high head developed by the centrifugal pump. So, this implies that centrifugal pump with one impeller cannot be used to raise high heads. So, ultimately, now to raise the liquid at much higher heads, we have to increase now the number of the impellers. So, more than one impeller are needed to develop the high heads. So more than one pumps or one impeller is needed to develop the high head. So the discharge of one pump, now what we can do, the discharge of one pump is delivered to the next for further increase in the head. So that means the discharge of one impeller or one pump, when we supply that to the another pump, so before that, or you can say in between these two pumps or the impellers, we have to properly guide that water to the inlet of the next one. Okay. So to guide that water in between, we use a row of guide vanes. Okay. So we have two different impellers. In between these two impellers, there is a one row of guide blades. Okay, and that whole system we enclose in a casing, and that becomes a multi-stage pump. Okay, so that becomes a multi-stage pump. So when water enters to the one impeller, there is increase in kinetic energy as well as the pressure energy of the water. After that, that high energy water goes to the guide vanes. So in the guide vanes, the kinetic energy is reduced, and that is converted into further enhancement of the pressure energy. So when the liquid or water is coming out from the guide vanes, the liquid has high pressure energy as compared to first one, but lower kinetic energy at the entrance to the guide vanes. So then water enters to the next impeller. So in the next impeller again, there is increase in kinetic energy as well as in the pressure energy. Okay. And again, at the outlet of second impeller, the water comes out with high pressure energy as well as kinetic energy. That high kinetic energy is again converted into the pressure energy when it passes through the casing. Okay. So ultimately, at the outlet of the pump towards the delivery side, we have a water or a liquid with high pressure energy but with less kinetic energy. That is our requirement. This is how this multi-stage pump works. Now you can also see in this diagram, okay, so we have the first impeller over here. Water enters from this side, okay. So water comes out from the impeller, then it goes to the guide vanes. Here is the rows of guide vanes. So after guide vanes, it goes to the eye of the next impeller, okay, and then it again comes out from the second impeller, okay. So this is how two different impellers and one row of guide blades is mounted on a single shaft in case of multi-stage pump. So when we talk about the energy transfer, see this diagram. So in this diagram, I have first impeller, okay. So this is my x-axis. So this is my first impeller, then the guide blades, then second impeller, and then casing or maybe another row of guide vanes. So when water enters to the impeller, first impeller, see here, when water enters to the impeller, its pressure energy increases. Okay, that means its pressure head increases as well as kinetic energy or kinetic head increases. Okay, so when it passes through guide vanes, you can see in guide vanes what happen. There is further increase in pressure head. Okay, at the loss of kinetic head. So in the guide vanes, there is a diffuser. There is an increase in cross-sectional area within the guide vanes. So that reduces the velocity, and that reduction is converted into high pressure head. Okay, and then again water enters to the next impeller. So when it goes to next impeller, again there is a rise of pressure head and there is a rise of kinetic head. Okay, then water goes to the another row of guide vanes or a casing. Again there increase in pressure head and there is a reduction in kinetic head. Okay, now you can see what happens at the outlet. So at the outlet we have water with some velocity VO and having pressure head this much. Some velocity VO and there is high head in the water, high pressure energy per unit weight in the water. Okay, so you can see also in the diagram, this is my HI, the head rise in the impeller. This is HG, the head rise in the guide vanes. Okay, this is up to here. Okay, so this is my one stage. This is my one stage, and this is my head generated in one stage. Then in second stage, this is my HI, head increase in the impeller from here. Okay, and in the guide blades up to here. Okay, so this is my another HT, head gain in second stage. So here the total head gain is 2 times HT. So this is my multi-stage pump. So in case of multi-stage pump, now you can write the total head gain. Okay, or you can say total head developed. That is equal to N times HI plus HG. So N is the number of stages. Okay, or the number of impellers. or the number of stages. So this I can write as n times ht. So ht is my total head rise in one stage. Okay. Hi is the pressure head rise in one impeller, and hg is the pressure head rise in guide wings. Okay, so this is how I can find the total head develop in the multi-stage pumps. The next is the pumps in parallel. Now this type of arrangement we need when we need at the outlet high discharge. Instead of high head, when at the outlet we need high value of Q, so this type of arrangement is used. So this is called the parallel arrangement of pumps. Okay, so in this case, each pump lifts water from the common sump and discharges into the common delivery pipe. So here you can see this is the common sump and the water delivers to the common delivery pipe. Okay, so here the total discharge is given by the sum of the discharges of individual pump. So you can see here, so the total discharge I can write as the Q1 plus Q2 and so on. Okay, so this is what happened in this arrangement. Okay, then next is the specific speed of a pump. So as in case of a turbine, the specific speed of a pump is used to compare the performance of different types of pumps. So similar to turbines, we have a concept of specific speeds in pumps also, and in pumps it is used to compare the performance of different types of pumps. So specific speed of a centrifugal pump is defined as the speed of a geometrically similar pump that delivers a unit quantity of water against a unit head against a unit head, okay, under corresponding conditions of working, that are the similar conditions of working. Okay, so here we have the unit quantity, the unit discharge against the unit head. So that is the specific speed of a pump. So now I am going to derive this formula for the specific speed of a pump. So now I have U equal to pi d n divided by 60. So from here I can write n 60 u divided by pi d. So I can say now the n is proportional to u upon d. Okay, so n is proportional to u upon d. Now I have another formula for discharge. that is K times pi dB into Vf. So I can write discharge is proportional to dB into Vf. So further N is equal to B upon D, this ratio. Okay, so I can write B is proportional to D over here. So again I can write as Q is proportional to D square into Vf. Okay, so from here I can write D is proportional to Q upon Vf under root. Okay, now further I have flow ratio, that is Vf divided by under root of 2gh. So I can write Q again, sorry, D again. D is proportional to Q upon Kf under root of 2gh. So this is further in under root. Okay, so this I can write as D is proportional to Q. So when I solve this, it becomes Q divided by h raised to power 1 by 2 within the under root. Okay, then next I have one more formula for Ku, that is U upon 2gh under root. Okay, so from here I can write U as Ku under root of 2gh, and further U is proportional to uh, Ku is constant, 2g is constant, proportional to under root of h. Okay, so now I use these two values of d and u into this equation. Put these two values of d and u into the formula of n. So now I can write as n is proportional to under root of h divided by q upon h raised to power 1 by 2 under root. Okay, this is further proportional to under root of h divided by under root of q into h raised to power 1 by 4. Okay, further I can write it as h raised to power 3 by 4 divided by under root of q. Okay, now further I can write it as n equal to now the constant of proportionality h raised to power 3 by 4 under root of q, where c is constant now, constant of proportionality. So now I use here the definition of specific speed. So according to that definition, when h and q they are reduces to unity, okay, my speed becomes equal to ns. Okay, so now you can see here in this formula, when h and q becomes 1, my n becomes equal to ns. So that means the value of constant now is equal to ns. Okay, so put this value of constant into this formula. So now I can write as n is equal to ns h raised to power 3 by 4 under root of q. So now you can write ns is equal to n under root of q h raised to power 3 by 4. So this is the formula for specific speed of a pump.